All right, this is the section 3.5, Graphs of Functions, pre-class notes. There are two major objectives that we want to cover in this. We want to determine algebraically if a function is either even, odd, or neither, and we want to learn how to piecewise functions. We will be doing transformations of functions on the in-class notes, but this is just some information we need from this section as well. So in this section, we will discuss aids for sketching graphs of certain types of functions, but in particular, we want to talk about two types of function characteristics. A function f is called even if f of negative x equals f of x for every x in its domain. What this really means is that anytime you plug in x and the opposite of x, so if say we plug in 2 and negative 2, we get the same output for our y value. That means that even is the same thing as having y-axis symmetry. So notice that's respect to the y-axis symmetry. A function is called odd if when you plug in a negative x into the function, you get the opposite value of y than you would have originally. So say you had the ordered pair 1, negative 3, then you would also have the ordered pair negative 1, 3. So plugging in the opposite of your x gives you the opposite of your y. And that means that odd means that we have origin symmetry. So we want to be able to test for this. So the test is when we plug in negative x into a function, if you can get the original function back, then you know that you have an even function. If you plug negative x into a function and you get the entire opposite of your original function, sometimes like a negative 1 through the whole function, then you know you have an odd function. If you plug in negative x and you don't get either of those two outcomes, then that function is neither even nor odd. So we're going to go through, and here's the test, just showing you what we were talking about there, just simplifying that a little bit. So we're going to do the following examples and determine if they're even, odd, or neither. So looking at this first one, I usually always start out with the test for even. So f of negative x, and actually we could just say even versus odd here, and then we could say neither if it doesn't work. But you're going to plug in negative x into all of the x locations of your function. Now, there's something to note that by definition of absolute value, so this is a special case here, anytime you plug in a negative under an absolute value, that's the same thing as if you plugged in a positive. So remember, absolute value of negative 3 is 3, absolute value of 3 is also 3. So we can swap this because of what it is. It's because it's an absolute value symbol. So because I got my original function back, that means that this function is even. Okay, so that is an even function. Let's look at my next example. So we're going to do even versus odd again. And again, if it doesn't work, we would say that it has neither. So we're going to plug in negative x into our function. So this is 7 times negative x to the 5th minus 4 times negative x to the 3rd. Now when you're plugging in a negative into things with exponents, you have to ask yourself, if I raise this to the 5th power, would this come out negative or positive? So if you raise a negative 1 to the 5th power, you're going to get a negative 1. If you raise it to an even power, you'd get a positive 1. So this is going to be negative 1 times a 7, so that makes that negative 7 x to the 5th. Then this is negative 1 to the 3rd power, so that's going to be a negative 1 times a negative 4, so that's going to be plus 4 x to the 3rd. Now this, if we pull out a negative 1, because it's not the original function, but if you factor out a negative 1, just to check, this is negative f of x. So that means that this function we were just looking at is an odd function, because it gives us the opposite of our y value. So that's showing you two very clear examples. One's even, one's odd. Now, we want to talk about a couple special cases, things that maybe either don't work or they're a little harder to check. So let's look at 12. So notice there is no x to plug in for. So f of negative x equals 12 still, because there's no x here. And 12 is the original function. So this is even because it didn't change anything. So all horizontal lines are going to be related to an even function with the only exception is f of x equals 0. This is actually both even and odd. And usually you can't be both. You can't be even and odd because that's y-axis symmetry and origin symmetry. But if you have just the line, the x-axis line is your graph. So if this is my actual line, that is going to have origin symmetry and both y-axis symmetry because it's not very interesting, but it also has all the properties you want. And a positive x and a negative x give the same y value. And if you have 1, 0 over here, you have the opposite of that on this side. You have negative 1, 0, which 0 doesn't change signs. That's kind of why this works. So any other horizontal line, f of x equals 3, f of x equals negative 2, those are all even functions. But f of x equals 0 is both. Okay, now this one's kind of interesting because if you remember from B, the one we just did a minute ago, you had two odd powers in the same function, whereas this has an even power, an odd power, and an even again, because if you don't have an x, you're an x to the 0. So the curious part is, will this work out? We want to know. So if I plug in a negative x, so I'm doing my even versus odd, and I plug it in for all x's in the problem, this is going to get squared. So negative 1 squared is actually positive 1, which means this stays positive 3. This is a first power though, so this is going to be negative 1 times negative 5. That's going to change signs. And then 1 doesn't have an x, so it's going to stay itself. So this is not f of x. If we pull out a negative 1 out of the function, it will change the signs of all our insides. This is also not negative f of x because this is the negative up front, but this did not turn out to be the original function. The negative 5 matched, but the other two signs were wrong. Just like up here, the negative 5 was the wrong sign because we had a positive 5 when we were supposed to have a negative 5. So if it fails both, if it's not going to pass either test, we say that it is neither even nor odd. Not all functions are going to have y-axis symmetry or the origin symmetry. And then our last one to test for even or odd on the pre-video before we do the piecewise functions is this one right here. So we're going to do the test. So even versus odd. So plugging in a negative x, this would be negative x cubed minus 1 over negative x. If we cube a negative, that's going to still be negative. This is negative times negative, so that's going to be positive. So that is not my original function. It has the wrong signs, but both signs are wrong. So if we pull out a negative 1, you get the original function. So this equals negative 1 f of x, which means this function is odd. So that is how you test for even, odd, or neither. You plug in a negative x, and then you say, after I work it out, do I get the original function? If that doesn't work, I pull a negative 1 out of my answer and see if it's negative 1 times the original function. If I get that, it's odd. If I get neither of those situations working, it's neither. Okay, so then the last piece of the pre-video is that we want to talk about how to graph piecewise functions. And we're going to do this in the most simplistic way possible. We're going to utilize what we know about table of values. If you're very familiar with the shape of these functions, you can get by with knowing how to do some of the stuff we're going to do in class, which is transformations of functions. But because this is very dependent on the domain of the function, it's really important to know how to set up maybe 3 separate tables and graph these by hand. So we call functions where you have different graphs on different domain restrictions piecewise defined functions. So this one has 3 separate pieces. We have y equals negative 2x if our x's are less than negative 1. We have y equals x squared if our absolute value of x is less than 1, which we want to rewrite that because that's kind of a vague way to say our domain there. This is what we learned about when we did inequalities. Absolute value inequalities where you have a less than and a positive number, you turn it into the inside of the absolute value is between the negative and the positive of the number. So this really means between negative 1 and 1. And then we graph y equals negative 2 if x is greater than or equal to 1. So I usually write these as 3 separate equations with their domain information. And I'm going to do a table of values for each. So y equals -2 when x is greater than or equal to 1. Now, the only thing that usually gets people when they do a table of values for piecewise functions is that a lot of times people will struggle with knowing if you're supposed to include the endpoint or not. So you should always include the endpoint in your table, regardless of if this is an equal to or not. And the reason for that is there's going to be points between -1 and 0 that we want to make sure we include in the graph. Even though -1 is technically an open endpoint, we don't want to leave it out because we miss every number between -1 and 0, because 0 would normally be the next thing, or -2. So say this is less than -1. -2, you'd miss all those numbers like -1.1, -1.256. So we have to make sure we include our endpoint, but make a note if it's an open or closed endpoint. That way you know if you're drawing an open circle or a closed circle. Every other number you include is just going to be a regular dot. It's not open or closed, it's just a point. And less than -1 means -2, -3, -4. You can do as many as you need, but this pattern is going to continue because there's no stopping on the other side. So if I plug in -1, that's going to be -2 times -1, so that's +2. -2 times -2 is +4. -2 times -3 is +6. And -2 times -4 is +8. So I'm going to go ahead and graph this specific piece before I move on. So -1, 2, I'm supposed to have an open circle. And then -2, 4 is just a point. -3, 6 is also just a point. -4, 8 is a point. But this is a linear equation. It's mx plus b format. So this is just drawing a line that continues forever as my x's get smaller. So we could grab any point out here and find a point on that line. So that's the first piece of my piecewise function. So this is part 1. You don't need to label the 1, 2, 3 that I'm going to do. This is just to show you where the pieces are popping up. So then x, y chart again for piece 2. So I'm again including my endpoints and every integer between them. I'm just making note that the endpoints are either opened or closed. So neither one of those had equal to. So they're going to be open endpoints. Plugging them into my function, so -1 squared is 1, 0 squared is 0, 1 squared is 1. So -1, 1, I'm supposed to have an open endpoint. Try your best because see, it's hard to draw on this. 0, 0 is just a point, and 1, 1 is another open endpoint. And this is a parabola because I know it because it has that x squared feature. So it's a little piece of a parabola. So that's piece 2 that I just graphed. Okay, so piece 1, piece 2. And again, I don't want to see the 1s and 2s on your paper. This is just for emphasis, okay? And then x, y, again, for y equals -2, when x's are either equal to 1 or bigger. And this pattern also continues down forever. So this would be a closed endpoint because it does have the equal to. And then we plug in. Now the thing is there's no x in our equation, it's just -2. So that means it's a fixed value forever, no matter what x you plug in. So this is a horizontal line. So 1, -2, closed endpoint. Make sure that's nice and closed. And then we're gonna go, oop, it didn't want to stay. Sorry, sometimes when I draw points using my pen, it doesn't want to recognize them. Okay, so then this is closed. That's another point, another point, another point. So this is a horizontal line and continuing in that part, and that's portion 3. Now what you'll note once you've graphed your piecewise function is that it should still pass the vertical line test. Anywhere we had overlap, one of the endpoints or both of the endpoints should be open. So you never use 1x more than once. So that is our first piecewise function. I want to do one more, and then this will be the end of the pre-video for this class session. So I'm looking at, this one is y equals x minus 3 if my x's are less than or equal to -2. Y equals -x squared if my x's are between -2 and 1. And y equals -x plus 4 if my x's are greater than or equal to 1. So we're going to start with our xy chart. So -2 is equal to, so this will be closed endpoint. Sometimes I'll just abbreviate CE or OE for closed or open. And then I'm going to pick numbers smaller as well. So -3, -4, -5 continues forever. And then we plug them in. -2 minus 3 is -5. -3 minus 3 is -6. -4 minus 3 is -7. -5 minus 3 is -8. And I'll go ahead and graph that. So -2, -5 with a closed endpoint. Try to make sure that's nice and closed. And then we're going to plot -3, -6, -4, -7, -5, -8. So this is a line that has a slope of +1/1, and if I continued drawing it, it would cross at -3, just like a regular line, but we're only graphing a piece of it. All right, so now we're going to do our middle. Now this one we have to use all the endpoints, whether they're opened or closed, and I usually do every integer in between if I have a start and an end. Unless this is a really big gap, then I might do like every other or every third number in between, just depends. So this is open endpoint for both of these because neither one of them have an equal to, but we still need to know what they are. So be careful with this guy. This is negative, then your number squared. So that's actually 4 times a -1, so that's -4. And then -1 squared is 1 times a -1 is -1. 0 squared is 0 times -1 is still 0. And 1 squared is 1 times a -1 is -1. So we have -2, -4 as an open circle. And then we have -1, oops, didn't stay. Sorry, sometimes my pen does not want to draw what I want it to draw. -1, -1, 0, 0, and then we have another open endpoint on 1, -1. Okay, so this is a parabola, again, because it has that x squared. So we've got that one graphed. And then the last piece is another linear equation with a -1 slope this time and a +4 if we were crossing the x-axis at the y-intercept, but we're not, because we are going to start our x values at +1 and continue upward. So this one is a closed endpoint because of the equal to. So this would be -1 plus 4, so that's 3. -2, because you have to plug it into this x, plus 4 is 2. -3 plus 4 is 1. And -4 plus 4 is 0. So we have 1, 3 as a closed endpoint. Make sure that's nice and visible. And then we have 2, 2. It still wants to be open. There we go. 2, 2, 3, 1, and 4, 0. And this is a, again, linear equation continuing on forever. So piecewise functions do not have to be horrible if you just graph them as individual pieces on each provided domain using a table of values. The big things to look out for are making sure you do your endpoints correctly and that you use the range of values they tell you to plug in for X correctly. So that is it for our pre-video.